There we go.
I thought you were on. You saw the name in there.
All right, why don't we go ahead and get started? And people can trickle in as they come on. I think this week is SSA meeting, right? So some people may be tuned into that. But for those of you who are here, thank you all for tuning in to our IGPP virtual seminar this week. Obviously, we are very lucky and excited to have Professor Jean-Luc Margot with us from UCLA to tell us about his recent work on the planetary properties of Venus. Professor Margot received his bachelor's degree in electrical engineering from, I don't speak French, but from the Université Catholique de Louvain in Belgium, after which he attended Cornell University, where he received his doctorate in astronomy. He has held a number of different postdoctoral positions, including a stint at the Arecibo Observatory in Puerto Rico and as a fellow at Caltech, after which he became a professor at Cornell and then finally a professor at UCLA, where he has been since 2009. He's received numerous honors for his research accomplishments, including being awarded the Knight of the Order of the Crown of Belgium, and he even has an asteroid named after him. So please give him a warm IGPP welcome. And Professor Margot, I will turn it over to you.
Thank you, Catherine. Thank you for the invitation. It's exciting to be here virtually with you all. Today, I'd like to describe almost 15 years of radar observations of Venus and what we're trying to measure in terms of its spin state and moment of inertia. Just in case we have a major Zoom meltdown, I thought I would put the major results on the first slide. I'll be describing an Earth-based radar speckle tracking technique that gives us 5 parts per million precision on measurements of the instantaneous spin state of Venus. And with that technique and our observations over the past 15 years, we've improved the knowledge of the spin axis orientation of Venus by about an order of magnitude in each dimension. We've refined the obliquity, and we've obtained the first measurement of the spin axis precession rate, which yields the moment of inertia of the planet. On that basis, we can obtain a rough estimate of the core size. We also have new estimates of the average spin period of Venus over the interval of our observations. But more importantly, we found that the spin period changes by quite a bit, by 20 minutes or so. And I'll show that the process responsible for this are atmospheric angular momentum variations. And we can quantify by how much the atmospheric angular momentum varies on the basis of our observations. There's a possible diurnal forcing of the variations we observe, and that may be related to mountain torques. And then finally, I'll describe the fact that these length of day variations cause a challenge for predicting the positions of landmarks in inertial space. And I'll quantify that as well. So the motivation for measuring the spin state of Venus is illustrated on this slide. We've learned an incredible amount about our planet and the interactions between its fluid layers by monitoring the spin of the planet, both in magnitude and direction. And this technique is powerful because very often the forcings are known, and we can measure the response of the planet in both amplitude and phase to eliminate various geophysical processes. We can do the same thing for planetary bodies. And I want to emphasize the importance of planetary interiors. If you want to understand pretty much anything about a planet, it's really important to understand its interior structure. For instance, the atmosphere is the history of outgassing from the planet. The geology on the surface is the manifestation of forces in the interior. The magnetic field depends on the interior properties. And also in terms of understanding the origin and evolution of planets, it's really important to have a good picture of the interior structure, the pressure and temperature profiles that then dictate the thermal evolution of the planet. And we're in this interesting situation where our sister planet, the planet that's closest to Earth in terms of mass, size, and density, there's a big question mark about its interior structure. The size of its core is not known. And so that's what we're going after. What I'm showing on this slide are the polar moment of inertia, normalized polar moments of inertia of the terrestrial planets. And the picture as of a few years ago. And then with the technique that I'm using for these observations, we were able a few years ago to quantify the moment of inertia of Mercury. And for the first time, being able to have some sort of preliminary reference Mercury model for the interior structure of that planet, which is really satisfying and allows us to learn more about this planet and its interior processes. So we want to do the same thing at Venus. So let me get some terminology out of the way. I'll be using moments of inertia, A, B, and C, where C is the largest moment of inertia, which represents the distribution of mass inside the planet. And then I'll be using coefficients in the spherical harmonic expansion of the gravity field. And in particular, I'll be using the J2 in this case, or the C20 coefficient, which is the difference between polar and equatorial moments of inertia of the planet. So if we want to measure the orientation of a planet, we can consider this example for Earth. What you would want to do is create a terrestrial reference frame based on the positions of Earth receiving stations, such as GPS station, radio observatories, and so on and so forth. And then you would want to orient that frame in an inertial frame, the celestial reference frame that you might create based on the position of distant radio sources, such as quasars. And in order to relate these two frames, you can perform a succession of rotations. And I'm showing here 3 rotation matrices, precession and nutation, showing the motion of the celestial, of the pole on the celestial sphere. You have a rotation matrix for the spin component along that axis. And finally, you can also have polar motion, which represents the position on the Earth's crust where the spin axis pierces the crust. So I'll go over these components of the matrix, of these 3 rotation matrices, to give you a sense of what we can learn from measuring these motions. So the first one, this precession and nutation motion shown here, is the forced precession of the spin axis. It's related to the fact that the Earth is slightly oblate as a result of its spin. So it's a little bit wider at the waist and shortened along the spin axis. And there's a solar torque and a lunar torque acting on this permanent deformation that generates this precessional motion. Now, the equation for the rate of precession is actually fairly simple. It depends on the mass of the perturber. It depends on the difference between the polar and equatorial moments of inertia. There's an n square mean motion square dependence that's 1 over a cubed. It's a distance dependence essentially. And then we have the spin angular momentum in the denominator. For Earth, all of these quantities are known except for the C minus A. So if you can measure the spin precession rate, you can measure the C minus A over C, which is about 1 in 300. We also know the J2 of the Earth based on tracking of satellites, for instance, and therefore we can obtain a value of C over mr squared, the moment of inertia of the Earth. So I'll be using the same technique for Venus today. Now, the second rotation matrix is the spin component, and there are a variety of influences there. The first, there are secular spin rate variations, which we've been able to quantify in part because of the timing of eclipses and the fact that ancient civilizations wrote down the timings that we can use today to estimate that secular evolution in the spin of the Earth. There's also a contribution to that secular component due to the change in the J2 of the Earth due to post-glacial rebound. And then on top of these secular variations, there are spin rate variations on all kinds of timescales that are indicative of a variety of geophysics. And in particular, there are long amplitude variations at decadal timescales, and these amplitudes are so large that they cannot be ascribed to the atmosphere or the oceans. There's just too much angular momentum involved there, and so they're suspected to be due to core mantle boundary interactions. And there's some observational evidence that suggests that indeed those decadal length of day variations can be ascribed to core mantle variations. And then finally, this third component, third rotation matrix, polar wander, is shown here. There's first an effect illustrated by Tommy Gold with a beetle walking around the Earth. And what he's trying to illustrate there is as the mass is redistributed inside the Earth tends to push the excess mass towards the equator to maintain principal axis rotation. And that motion has been observed on Earth. And also, there's the Chandler and annual wobbles that were predicted on the basis of rigid body rotation equations, but were found at a slightly different period than predicted by rigid rotation, which is an illustration of the fact that there's an elasticity inside the Earth. So we can measure these motions and quantify these rheological properties of the planet. So here's a little bit of a summary with the timescales of the processes that I've mentioned and the geophysical processes that can be ascribed to each one of them. And then in terms of length of day variations, again, a wide variety of timescales, processes such as tides, atmospheric angular momentum, El Nino, core mantle torques, and the geophysical significance. So I like to mention this quote from Monk and MacDonald's textbook. Diversity of the subject is appalling. It touches on every branch of geophysics. And in particular, both of these authors had UCSD and UCLA connections. So that seems appropriate to mention it. So my first set of takeaway messages: the rotational dynamics reveal interior structure, processes, and mechanical properties of the planets. We can learn about moments of inertia, core-mantle boundary interaction, atmospheric angular momentum variations, and viscoelastic properties of the planets. And it behooves us to establish a rotation service, very much like the Earth rotation service, to learn more about planetary bodies. So let me talk about Venus now, our sister planet. There are probably billions of Venus-like planets in the galaxy. And the main puzzle that we still don't know its moment of inertia or the size of its core. There was a paper a few years ago by Dumoulin et al. That tested a variety of composition and temperature models to understand the full range of possible interior structures and moments of inertia. And I've highlighted the moments of inertia in red. So these model predictions span a fairly wide range of values. And one of the conclusions of that article was that the traditional assumption that Venus's core is liquid may not, in fact, hold. We've used the Konopolev and Yoder's measurement of the K2 value for decades to support the claim that the core of Venus is liquid. But in fact, the recent paper by Dumoulin et al. Shows that there are, in fact, models where the core is solid that could also match that K2 constraint. So we don't know the size of the core of Venus, and we're not actually certain about whether the core is liquid or solid. The measurement approach that we're using to learn more about the core of Venus is shown here. It's the spin precession. And I've rewritten the equation to illustrate the J2 here, and the fact that the only unknown quantity in this equation is the C over mr squared, or the moments of inertia, right? We know the mean motion, we know the spin rate, we know the obliquity, and therefore, if we can measure the spin precession rate, we have a direct measurement of the polar moment of inertia. So here are some of the numerical values that I'm using, and we find that the predicted precession rate is something like 45 arc seconds per year, which translates into a precession period of about 29,000 years, not too different from Earth. The big difference with Earth has to do with the fact that the obliquity of Venus is so small that the motion that the spin axis traces on the sky is actually tiny. So we're talking about a motion of about 2 arc seconds per year. And in order to measure that with precision, requires both patience and high precision observations. So it's a challenging measurement to do. The observational strategy that we're using is illustrated here. So we use the 70-meter Goldstone antenna to transmit a monochromatic wave at 3.5 centimeter wavelength. And we record the radar echo at Goldstone, but also at the 100-meter Green Bank telescope in West Virginia, which is located 3,000 kilometers away. Now, the radar echo is speckled, as you can see on the bottom diagram, which shows the echo power. This is actual data showing that the total power that you receive has this random-like appearance, and that's due simply to the fact that the echo is formed by the contributions from thousands of individual scatterers on the surface of Venus, each of which responds with a specific amplitude and phase. And therefore, there's constructive and destructive interference, which gives rise to this random-like pattern and what we call the speckled nature of the radar echo. But what's important to realize is that this response is not random. It is very much dictated by the positions of the scatterers on the surface of Venus. And as Venus rotates, the speckle pattern rotates with it. So on this slide, I'm showing the speckle pattern recorded at Goldstone, and I've shifted the speckle pattern received by Green Bank 20 seconds later. And you can see that there's in fact a high degree of correlation between these two speckle patterns. So that's the technique we're using. We're sending monochromatic wave, recording time series at both telescopes, and then computing the cross correlation between these two waveforms. It turns out that this effect was known for a long time, has been known for a long time. Paul Green, in fact, in the 60s, drew this diagram showing contours of constant electric field strength on the surface of the Earth, and these represent the speckles. And he showed the position of two receivers, R1 and R2, the baseline between them, shown by this vector here, and the velocity of the speckles, or the trajectory of the speckles on the Earth. And he showed and described the fact that if the velocity was sufficiently aligned with the baseline, then there would be a high degree of correlation between these echo time series, and that you could infer important properties about the spin rate of the planet that way. Now, this technique was publicized by Igor Holin, a theoretical scientist in Russia who studied laser speckles. And he emphasized the fact that this technique could be used to measure planetary spin state. And we've then applied this technique to Mercury and now Venus, as well as Europa and Ganymede. So the first observable that we obtain is the epoch of maximum correlation. Here I'm showing the trajectory of these speckles at different times. And you can see that at t-1 hour, the speckle trajectory is not aligned with the two telescopes, and therefore the two telescopes record different time histories of the radar echo, and these echoes will not correlate. But at a specific instant, the speckle trajectory is nicely aligned. And because we know the positions of the telescopes, because we know the orientation of the Earth to high precision, we can then learn about the spin axis orientation of Venus. So this epoch, the time of day at which this correlation takes place, is a direct measurement of the spin axis orientation. Now, we're sensitive to one component of the spin axis, and I'll describe that in a moment. Here's an example. This is, again, actual data from the telescope, where I'm showing the complex correlation of the Goldstone and Green Bank echoes as a function of time from the data taking start. And most of the time, low-level correlation, but then there's a dramatic increase in correlation when the speckle trajectory is aligned with the telescope baseline. Now, we can measure the centroid of this Gaussian fit here, shown in red, to a much better precision than the width of the Gaussian itself, which is a standard result in statistics. And so we can, in fact, measure the epoch of correlation maximum to something like 0.3 seconds. The whole correlation itself lasts only about 30 seconds. So you have to have everything working just right during that time. Otherwise, your experiment fails. I have the data here just in case they're needed. But on this slide, I'm showing the 21 observations that we made between 2006 and September of 2020. And each one gives us a very sensitive measurement in one dimension, but not in the orthogonal direction. And that's because the trajectory of the speckles lies in the plane that is perpendicular to the component of the spin that is perpendicular to the line of sight. So we have good sensitivity to that component, but not to the orthogonal component. And as a result, we have these very narrow error ellipses on the celestial sphere that I'm showing here, color-coded according to the date of observation. And they all converge on one point of the celestial sphere if I include a precession model. If I don't include a precession model, they don't converge. And also shown here is 100 years worth of precession. These black dots represents the precession between 1950 and 2050. So our solution for the spin axis orientation of Venus is shown here in black with the 1, 2, and 3 sigma contours. And I'm comparing it to previous best estimates from the Magellan mission. There are the Davies et al. 1992 positions based on the radar imaging of landmarks and the solution of the geodetic control network. And then there's a measurement based on the solution to the gravity field by Konoplith et al. Now, at first glance, it seems like our measurements are only marginally consistent with these two estimates. And that's because these measurements have not been precessed to J2000, which is the reference epoch that I'm using. So if I precess their measurements, we then find that there's a very nice agreement. So I'll shift back and forth between the non-precessed and the precessed measurements. Oops. So we find very good agreement, in fact, with both of these estimates once precession is taken into account. And again, we've improved that knowledge in the spin axis orientation by a factor of 10 in each dimension, roughly. Now, in the model, I have a 3-parameter model for the spin axis orientation. One is right ascension, the other one is declination. And the third component is the precession rate, deep psi dt, so, which is shown here. So I jointly estimate these 3 parameters from the data. And we find that the precession period is about 45 arc seconds per year. And that's a direct measurement of the moment of inertia. So here's a result of a bootstrap analysis showing the range of moments of inertia that we obtain on the basis of our measurements. And we're finding a value of 0.337 with 7% uncertainties. Now, these uncertainties are larger than we would like, but they will go down as we continue our observations. On that measure, on that normalized polar moment of inertia basis, we can solve for a 2-layer uniform density model. This is a very simplistic model of the interior of Venus, where we consider the bulk density and the normalized moment of inertia that we've just measured. And we have 3 unknowns, the radius of the core, the density of the mantle, and the density of the core. So we have to set one of these unknowns to a specific value. And we've chosen to set the density of the core to a specific value, which turns out to be within 1% of all the interior models in the paper by Dumoulin et al. If we do that and solve this model, we find a radius of the core that's approximately 3,500 kilometers and a mantle density that's approximately 4,000. Now, I should emphasize that there are large uncertainties on these estimates for 2 reasons. One, this model is too simplistic. There's compression in these at high pressures, and so the uniform density assumption is incorrect. And also the 7% uncertainties currently result in large uncertainties. But again, that's the end goal is to obtain an estimate of the radius of the core by continuing to drive down the uncertainties. Now, what are the prospects from doing this from spacecraft observations? It actually is very difficult to do. So here I'm simulating a new mission in 2040 that would give you a measurement of the spin axis orientation, let's say with infinite precision, shown here in red. So between Magellan and 2040, you would have about 50 years worth of precession, which is about 100 arc seconds. And remember, the best Magellan estimate has a 14 arc second uncertainty associated with it. So you would detect that precession with 14% uncertainties at best. And right now we have 7% uncertainties with our ground-based measurements. If you consider a 5-year orbiter that has a radar system with 30-meter range precision, for instance, you would detect over that 5-year period about 10 arcsecond motion, and that corresponds to about a 300-meter displacement on the surface, which with a range precision of 30 meter give you about a 10% uncertainties at best. And I'll point out later that this is going to be more challenging than it looks like on paper, because this signal is actually going to be buried in a rotational noise that is considerably larger than what you're trying to measure. And then finally, if you had let's say a 60-day lander on the surface, the precession during that period would be about 10 meters. And if you could detect that with 0.5 meter precision, you would, again, get about 5% precision or so. So a challenging measurement to do even with spacecraft. So the second part of my talk here, the sort of takeaway messages: we've improved the spin axis orientation. We have a new measurement of the obliquity of Venus, measurement of the precession rate, moment of inertia, and a nominal core size for the planet. I want to talk now about another puzzle related to Venus, and that has to do with its length of day. It turns out we don't know the length of day very well. On this slide, I'm showing 3 estimates of the average rotation period of Venus. One shown here, obtained by the Magellan team on the basis of Magellan radar imaging. Then in 2012, Mueller et al. Combined the Magellan measurement with the position of features in the IR from Venus Express to infer an average rotation rate between the Venus Magellan epoch and the Venus Express epoch. And that estimate is shown in red with its error bars. And then finally, by combining 29 years of Earth-based radar imaging observations, we also obtained an estimate of the rotation rate shown here in green. So there are discrepancies between these estimates, and we want to learn more about the spin period of Venus and what might cause length of day variations. In addition, Venus is an interesting spin state. It has a 243-day retrograde rotation, which really shouldn't be there. If you think about tidal despinning, the planet should synchronize to its orbital period on 100 million timescales or so. And what maintains this odd rotation of Venus is likely related to torques on the atmosphere, which was first proposed by Tommy Gold and Steve Soter, where the process is that there's essentially a bulge in the atmosphere that is in the opposite direction than the bulge in the solid body, and that the torques on these two counteract one another, and that the spin rate sort of stabilizes where the torques match one another. So the solid body torque is not very dependent on the rotation rate of the planet, but the atmospheric torque is very much dependent on the spin rate. And so there might be an equilibrium value there where the Venus spin period settles. However, that process is not really well understood, or what happens when there are deviations from that state, on what time scales does it return to that state, and so on and so forth. So we're using our technique to measure the instantaneous rotation rate of Venus. If you recall, during that 30-second period where there's high correlation in our radar echoes, the baseline is well aligned with the trajectory of the speckles. And during those 30 seconds, we can actually measure the time lag, how long it takes for the speckles to travel from one telescope to the next. And that's a direct measurement of the spin rate of Venus. So here's an example correlation where I'm showing now not the epoch, but the time lag, the value of the time lag. It's about 20 seconds. And again, we can measure the maximum with a much smaller precision than the width of this function. And we in fact measure them to something like 1/10 of a millisecond. So our measurements are shown here in blue with their error bars. The date of observation is at the bottom. So this is spin period in days. And I'm showing the previous estimates of the average rotation rate from Magellan in yellow, from Magellan plus Venus Express in red, and from Earth-based radar imaging in green. So a few things should be immediately apparent. We can rule out a constant spin period for Venus with very high confidence. Most of our measurements are actually not consistent with the average rotation rate that have been published. And on the basis of our 21 measurements, we in fact determined a new estimate of the average spin period during the 2006-2020 interval that is shown here. Now, we also quantify the total excursion in length of day variations, and we find that the length of day varies by something like 61 parts per million, which corresponds to about 21 minutes. And there are a number of instances where we have measurements on consecutive Earth days. And so we can quantify the length of the excursion on that time scale as well. And that's 9 ± 5 parts per million, or about 3 minutes. We then consider the potential processes that could explain these variations. So first, we look at core mantle boundary processes with the Earth values shown at the left. We have a change of about 4 milliseconds in a 20-year period on Earth. We can translate that into a change in spin period. We know the moment of inertia of Earth, and that we can compute a torque. Now, if we assume that the core of Venus is liquid, and if we assume that it's going to experience a similar torque, it's going to be close, may not be exact, but it would be close. We find that we cannot explain the variations that we observe. It's in fact about 3 orders of magnitude too small to explain the length of day variations that we observe. So we rule that out as a primary mechanism. And the only remaining mechanism we rule out tidal despinning as well is atmospheric angular momentum. So we can attempt to quantify the atmospheric angular momentum at Venus. It turns out that is difficult to do because we know so little about the internal dynamics of the Venusian atmosphere. Here's an estimate from a recent review paper about atmospheric dynamics on Venus. I should point out that this estimate has large uncertainties, something like 30% or perhaps more. But we can use it to verify whether it could explain our observations. So let's consider a fractional change in atmospheric angular momentum epsilon. On Earth, if we took all the angular momentum of the Earth and dumped it into the rotation of the solid planet, we would change the spin rate of the planet by about 3 milliseconds. So we have a delta P of 3 epsilon milliseconds. On Venus, the change in period would be 9.4 hours. So our excursion in spin period variation corresponds to something like 4% change in atmospheric angular momentum, which is entirely reasonable. On Earth, we in fact observe changes on the order of 20% angular momentum. The big difference between Earth and Venus is illustrated here. So I'm showing the total angular momentum of the planet and the total angular momentum of the atmosphere and the ratio of these two quantities. There's a huge difference on Earth and Venus. The fractional atmospheric angular momentum on Venus is something like 60,000 times larger than on Earth. So the fraction of the atmospheric angular momentum that's contained in the atmosphere is considerably larger compared to the total planetary angular momentum. We then considered whether there are possible periodic variations, and one of the possibilities is a semidiurnal variation. So what I've done here is I've phased all the measurements according to a semidiurnal phase. Now, this is very strange. If this were confirmed, that would indicate that the spin period of Venus somehow slows down over a period of 58 days. And then there would be some impulsive release of an atmospheric angular momentum to spin the planet back up. And it's not at all clear which process could explain such a variation. A more plausible, perhaps, variation is a diurnal variation shown here. So again, I've phased our measurements according to the diurnal phase. And there's a hint of a periodicity there. I think it needs to be confirmed with additional measurements. But it's tantalizing. I'm also showing the position of topographic highs in the equatorial regions, Aphrodite Terra and Beta Regio here, to show the relationship between our measurements and these surface features. And the reason for showing that is that it's possible that this diurnal variation is related to mountain torques. That supposition is based on these remarkable discovery from the Akatsuki spacecraft of planetary scale features in the atmosphere of Venus. So there are these very large features, essentially as large as the planet itself, that are observed in the upper atmosphere of Venus and that are stationary with respect to the surface. So this is truly remarkable, right? These features are detected in the upper atmosphere that rotates faster than the solid surface by 60 times or so. And yet these features are stationary with respect to the solid planet. And there's a suggestion that they are in fact associated with these mountains on the surface. So these could be mountain waves that are launched by the interaction between the atmospheres and these mountain regions, especially in the equator, where you can see features that are associated with these topographic highs. Now, there's been an attempt at simulating how much you could change the length of day through these interactions between the mountains and the atmosphere. And so this is an article by Navarro et al. Showing the change in length of day in minutes as a function of the solar day. Now, this is a complicated story because what they're measuring, in fact, is shown in this solid line. So there's a tremendous amount of angular momentum loss in their study, which they then detrend to show this signature here. And so if you detrend that, you get this value here. And what we find is that these modeled variations are in fact 30 times too low compared to our observations. So there's currently a large discrepancy between the model results and our observations. There are a variety of reasons to explain this: model limitations, right? The resolution of this model is in fact much, much larger than the resolution, the scale of the topographic highs. There's this, angular momentum loss. The total angular momentum budget may be too low in that simulations. So there's a variety of issues. But in addition to that, this review paper that I mentioned earlier indicates that it's in fact extremely difficult to capture the dynamical state of the Venus atmosphere with precision. And so it's currently difficult to model this accurately. And again, we have very few measurements of the dynamics of the internal layers of the Venusian atmosphere. So we're hoping that our measurements can in fact help calibrate global circulation models of Venus, because we're providing a time history of length of day variations. Okay. I would like now to mention the impact of these length of day variations on future missions and measurements of landmark positions. We're using our spin period measurements shown here in black to constrain a continuous autoregressive moving average model of the evolution of the rotational phase of the planet. So I'm showing here 5 modeled trajectories in different colors. And on the next slide, I'm showing, in fact, 100 different rotational phase histories, right? So this is the rotational phase that you would measure with the length of day variations compared to the rotational phase that you would measure if the spin period of Venus were constant. And that errors grows roughly as a random walk. So there's a square root of t factor here. And it's large. It's a fraction of a degree after 10 years. It corresponds on the surface to about 3.3 kilometers on the surface after 10 years. So that's going to be a challenge for future measurements of landmarks and in fact targeting of missions to specific landing sites. So the takeaway messages for this part of the talk are shown here. We have a new measurement of the length of day on Venus. However, there are large variations in that length of day that can be explained to something like 4% change in atmospheric angular momentum variations. There's a possible diurnal forcing, which may be related to mountain torques. However, what we observe is currently an order of magnitude larger than what a GCM study has predicted. And then we find the rotational noise is going to be a challenge for future missions and future measurements. We are proposing a new orientation model for Venus to the International Astronomical Union. Some of you may be familiar with the standard way of documenting the change in spin axis orientation and the longitude of the prime meridian. Here's the current IAU model. I think that should say 9092 actually. And our proposed measurements, which now includes precession rates and a refinement to the spin rate and the orientation of the prime meridian. So if you want to do any work with Venus missions or future missions and register data sets to specific locations on the surface, you really need to have a good orientation model. So what are we doing next? We're going to continue our observations with Goldstone and Greenbank to try to beat down these uncertainties and improve the estimate of this spin precession rate, as well as quantify the length of day variation timescales and amplitude. We have proposed to use Goldstone in the Very Large Array to do similar measurements. The VLA has 27 antennas. However, the baseline is shorter and the signal to noise is smaller. So we're not exactly sure whether this combination is going to be more powerful or less powerful than the Goldstone GBT measurements, but it's worth investigating, and we're hoping to do that soon. And then we're also reanalyzing the Magellan radar data. We've developed quite a bit of software to reanalyze the radar data, redo a geodetic control network, but this time solving for the positions of thousands of landmark measurements and the position of the spacecraft simultaneously, which really wasn't done with the Magellan data, and resulted in these large uncertainties on the spin axis orientation. So we think that with this effort, we can actually substantially improve the knowledge of the spin state at the Magellan epoch and connect that new measurement to our existing measurements to improve the precession rate again. And I will leave my conclusions here, and I'll be happy to take any questions. Thank you.
Awesome. Thank you so much, Jean-Luc. That was a fabulous talk, very clear. And yes, we have plenty of time for questions. So just to remind everyone, you can either type your question into the chat box, or you can raise your hand with the raise hand function, and I'll call on you and you can unmute yourself and ask it. And let me open the chat box up here. I have a question to start while people are still absorbing. Oh, actually, I'll ask. Let Adrian go first. Go for it, Adrian.
Oh, thank you. Jean-Luc, that was fantastic. I just cannot believe the kinds of measurements you've made from so far away and put together. And it's also a tribute to what it takes to, I mean, the investments that are required in personal and other resources over many, many years. We're so focused on smaller or shorter time periods. Specifically, the thing that was surprising to me were the standing waves. When we think about standing waves in Earth's atmosphere, they're much more the scale of the topographic features themselves. And yet these standing waves that you were observing were just massive. And I was curious, this may not be your primary goal, but given how important the atmosphere is in angular momentum, why do you see those kinds of huge features that are persistent with much generated by small mountains, essentially?
Well, thank you for the kind comments. I should emphasize that the observations of the waves in the upper atmosphere are completely different from my observations. This was a Japanese spacecraft mission, so I have very little to do with those. We're just connecting our measurements of the length of day variations and hypothesizing that one potential process for explaining the variations is related to these gravity waves. Why are these features so large, I guess is your question, compared to the scale of the mountains? They must, this is not my area of expertise, they must amplify as they propagate upwards in the atmosphere. That's my hypothesis, but again, that's not my work and not my area of expertise.
Thank you.
I would like to comment on some of the other things you said. So in terms of resources, I forgot to mention the amount of time for a single measurement is actually not that large. We have a 45-minute session on the Green Bank telescope, and that's sufficient for us to do all the setup, the calibration, the measurement itself. So we could, in fact, do these measurements more frequently if we could obtain time on the Goldstone antenna, which is, its primary purpose is to do telemetry to spacecraft missions. So we've had some difficulty obtaining time on the Goldstone antenna for these measurements. And in part because it's Venus. For some reason, Venus has not gotten as much importance in the eyes of the DSN schedulers as Mercury, for instance. We did similar observations with Mercury and had little difficulty getting time, but for Venus, we've faced a lot more opposition. And speaking of Mercury, I want to point out that our measurements with this technique were confirmed by the MESSENGER mission to about 1%. So even though we're very far away, we are able to make very accurate measurements that can be confirmed by spacecraft.
Thank you so much. Thank you for.
David, I think you have a question. Go for
it. Yeah, that was a great talk. I really enjoyed that. And I have lots of questions, but my first question is, there's been a proposal to put a radar interferometer around Venus to measure changes in crustal motion due to volcanoes and so on. And of course, there'd have to be corrections for the atmosphere and the rotation rate. Would that add anything to your measurements, or is that still in the noise of your measurements?
Oh, I'm very much in favor of a mission to Venus, and in particular with a high resolution radar system. There's actually a paper, I think currently in review at GRL, where they attempt to estimate how well they could recover the spin axis orientation and precession. To their credit, they actually went back after they saw my preprint and changed their simulation scenario because they had initially assumed a constant spin period. Now, they've assumed that the spin period changes every 2.5 days, which turns out to, it's an improvement compared to this constant spin period assumption, but it turns out there are variations within those 2.5 days that compete with the range resolution. So it's a little more complicated, and I think you would need another simulation to really capture all those effects. But I'm optimistic that a future mission could indeed tell us a whole lot about Venus, and in fact improve some of our measurements.
Yeah, the repeat cycle would be 243 days, which would probably not be great for your kind of thing, but yeah. No, great talk. I was going to ask you also about the state of the core, whether you think it's liquid or solid, or maybe your data don't tell you anything because the atmosphere has overwhelmed the signal.
Right. Our data cannot inform us about the state of the core, unfortunately. My gut feeling is that there's, circumstantial evidence that the core is liquid.
Yeah, sure.
But it'd be nice to have a confirmation, right?
Thanks. Great.
Yehuda, if you want to ask your question.
Yeah, hi, it was a great talk. I was wondering about, I was thinking about the recent InSight mission by the Mars lander where they put a seismometer on Mars. Is there any benefit from doing something like that on Venus?
That'd be phenomenal. I'm also all in favor of that. However, the technical challenges of doing that are considerable, given the high surface temperature and surface pressure. So it's listed in the Venus Exploration Analysis Group documents. It's listed as a quote unquote distant goal. So it's something that the community is considering, but I don't think we're there yet.
Well, I had a quick question, probably a little more basic question, but when you're taking these measurements of Venus, does Venus need to be close enough to Earth to get good measurements? Or is there a certain, you said you're doing this on Mercury too. So is there a certain place in the orbit around the sun that you can take these measurements and then not during another time? Or how does that work?
Yeah, that's a great question. The signal to noise of radar observations goes as 1 over distance to the 4th power. So the distance does matter. It turns out that because we have high power transmitters, high gain, and because Venus is so large, we do have most of the time, I should be careful actually. For a substantial fraction of the time, we do have sufficiently high signal to noise. We do need high signal to noise because we made these measurements on essentially 1 second integration time, right? So signal to noise does matter. A more important consideration actually is when that trajectory is going to be aligned with the baseline between the telescopes. And it turns out there are times of the year where if you wanted to do this measurement, you couldn't, because the spin axis is oriented in such a way that the spectral trajectory would never line up with Goldstone and GVT. So if you take these considerations together, I would say that we could do daily measurements on something like maybe 20% of the time.
Wow, okay.
If we wanted to.
Yeah. Cool, thank you.
Yeah.
All right, are there any other questions that people have? You can type them in the chat or raise your hand. I think we're just at time too. So if there's no other questions, let's thank Jean-Luc again for his awesome talk. Thank you again for joining us. We really appreciate it. And let's see, next week we'll have our virtual seminar, and I think we have Greg McClaskey from Cornell University speaking. So tune in for that next week. And thank you so much for tuning in today.
Thank you for having me. It was fun.
Stop recording.